Rutherford planned a special experiment in 1909 to verify the Thomson atomic model. No one expected this experiment to lead to the discovery of atomic nuclei or the development of surface analysis technology based on the experiment. Back in the day, Ernest Rutherford experimented with measuring the specific charge of the alpha particles. He did not hold a vacuum because he thought that the alpha particles were so heavy that the air would not affect the experiment. In contrast to this expectation, the phenomenon of alpha particle being scattered by the air inside the measuring instrument occurred continuously. The Thomson model was the most widely accepted atomic model at that time. This model describes an atom as an electron embedded in a large, positively charged particle. If the positive charges were uniformly distributed throughout the atom, as in the Thomson model, then the air molecules would not form a strong electric field. Further, this should not affect the experiment. However, the results were different. Under the suspicion that positive charges will be concentrated at one point, he conducted alpha particle permeation experiments for approximately 5 years from 1908 to 1913. In the experiment, alpha particles were sprayed on a thin golden film, and the alpha particles penetrating the film were observed on the surrounding fluorescent screen. These expectations were correct. If Thomson atomic model is correct, all the alpha particles should easily penetrate the thin gold film and be detected. However, among the alpha particles incident on the thin gold film were highly refracted, and alpha particles that bounced backward were also found. Based on the detected alpha particles, Rutherford proved through a logical explanation that positive charges are concentrated in a narrow area and that the location should be the center of the atom. In addition, a new model, called the Rutherford atomic model, was proposed in which electrons exist around the positive charge concentrated at the center of the atom. According to the Rutherford's experiment, alpha particles that scattered after collision have different energies and scattering yields depending on the material of the thin film and direction of scattering. Thin films can be analyzed using ion scattering spectroscopy. The greatest advantage of this method is its quantitative analysis. This is because scattered particles are always detected at the same energy and yield in a specific scattering direction when irradiating the alpha particles of the same energy and amount. The modern ion scattering spectrometer was developed to measure even minute variations in the energy of scattered particles, a further improvement over the Rutherford experiment that measured only the number of scattered particles. Ion scattering spectroscopy is classified into low, medium, and high energy ion scattering according to the incident ion energy, and the measurable depth and depth resolution differ depending on the energy range. Among them, medium energy ion scattering, or MEIS for short, has a measurement scope of approximately 20 nanometers and a depth resolution of approximately 2 angstroms for the atomic layer, which is remarkable. The MEIS provided by the HB solution is a time-of-flight analyzer and is called TOF-MEIS. TOF-MEIS consists of following components: an ion source that generates helium ions that are incident ions, a collimation lens that primarily focuses the ion beam, an acceleration tube to accelerate helium ions up to 100 kiloelectron volts, an E-cross-B filter that filters impurities other than helium ions, a pulsing module that generates pulse beams, a Faraday cup for accurate measurement of ion beam current, and an objective lens that focuses the ion beam on the sample, and generated pulse beams are incident on the sample on the manipulator. The MEIS spectrum is obtained by measuring the energy of the scattered particles from the sample using a TOF analyzer.